So here we are in the third lecture on structural analysis, chapter number 6, and in the previous lecture we solved a problem on truss structure, and then in the end we did one problem on frame. So this time we'll be solving some problems on machine, and so let's begin reading this problem. I'll take 1 minute so that you can read the problem carefully. This is 6-112 from your textbook. So we have this machine here. It is composed of a sector gear C and a pinion gear G, and to this small pinion gear G we have a arm attached. It is pin connected at the center of the pinion, and we are applying a force of 40 Newton at point D. And this force of 40 Newton is of course amplified through this machine structure, and it is basically exerting a compressive load on this cylinder S. So we need to find this compressive load that is exerted on this cylinder. So we know that while we were solving problem on truss structure, we use the method of sections. Okay, and when we solve problem on frame, the method that we adopted was to dismantle the parts. So we disconnected different parts, and then we analyze each and every part by using equations of equilibrium. So the same strategy is used in solving problems on machines. We have to actually think of dismantling or disconnecting these members one by one, and thereby calculating the unknowns, so that the problem is never statically indeterminate. So if you remember, when we were solving the problem on frame, I told you that if you will going to consider the entire free body diagram of the frame, your problem will become statically indeterminate. That is, you will have more unknowns and fewer equations of equilibrium. So that is why we have to dismantle each and every member of the frame or a machine to make them statically determinate. So the same strategy as we adopted in case of frame will be used here. And so we have to think that from where we will going to start our analysis, because we can clearly see that we have no known force or known load acting on this machine except this 40 Newton force here applied at point D. So since this is the only known force here, we should start our analysis from this part, that is the small gear G. So we draw the free body diagram. We dismantle this gear, okay, and we remove this pin. We take this gear, separate this gear from the rest of the structure, and redraw it and show all the known and unknown forces acting on it. So you see that at this point we have a pin. So I have shown two reactions of the pin here, Gx and Gy, and I have arbitrarily assumed their direction to be positive, that is in the positive x and positive y direction. Then at a distance of 0.5 meter from the center of this small gear, 40 Newton force was applied. So I have shown that force here. And one more thing was mentioned in the question, that the gear only exerts tangential forces between them. So you see that when two gears are basically meshing, and one gear is actually moving in a clockwise direction, then the other gear will going to move in the anti-clockwise direction, and there will be some interaction happening at the interface of these gears. So this line is basically a tangent line, and a tangential force will going to act on this line only. So this is the tangential force that is driving the gears, and this tangential force I have shown here. So again, the direction is arbitrary, and so we realize that following this figure, we realize that there is a tangent line between these two meshing gears, and on this tangent line there is a tangential force acting. So I have shown a tangential force here. Now the point to note is that there is no need of for calculating gx and gy in this problem. Okay, we do not want the values of gx and gy, so they are unnecessary, and therefore we should not involve them in our analysis. And the only way we can remove these two forces, spin reactions gx and gy, is to take moment about point G, which is the center of the small gear. And we see that the perpendicular moment arm of 40 Newton force is 0.5 meter from point G, and the perpendicular moment arm of this tangential force is basically the radius of the gear, that is 0.2 meter. So this is also perpendicular at this tangent. So this radius line, this radial line is basically a normal to this tangent, which is the line of action of this tangential force. And this is the force Ft, which is actually driving this sector gear. So in order to find the value of Ft, we can simply take the moment, sum the moment about point G, and in doing so we realize that Gx and Gy will not going to produce any moment about point G, because the line of action is passing from point G, and so the moment arm for Ft is 0.2, and this Ft is basically exerting a anti-clockwise moment about point G. So that's why we have a negative sign appearing here, and this 40 Newton force is exerting a clockwise moment about point G, which according to our sign convention must be positive. So there is a positive sign appearing with this moment. And solving this equation, we get the tangential force to be 100 Newton. Now, just to remind you people, if you are not familiar how to calculate the rotational sense of a moment in 2 dimensions, then there is just a simple trick. Okay, you just have to extend the line of action of this force, and from this point where you are trying to calculate the moment, you draw a position vector, which is the moment arm, okay, R. And what you do is that in your imagination you just bring this 40 Newton force, preserving its direction, and joining the tail of this 40 Newton force with the tail of the moment arm or moment arm vector R. Right, so this is your 40 Newton force now, and this you are doing in your imagination. So and then what you do is you just make a curl from this R towards this F, and this curl will going to give you the rotational sense of the moment which is exerted by this 40 Newton force about point G. And as you can see that this curl is indicating that this moment is clockwise. So this moment is clockwise, that is why positive. So this is how you calculate the rotational sense. And since we have calculated the tangential force now, the next step is to move forward. That is, we have to take the analysis from this small pinion to this sector gear now. So we have to draw the free body diagram of this sector gear, or the equilibrium of gear C, you can call it. So you see that this pinion, this small gear, was actually a meshing part with this sector gear. So I have shown the direction of Ft like this, on this part. So because of Newton's third law, I have to show the direction of Ft on this sector gear in the reverse direction. Okay, so that when these two parts are combined, internally Ft cancels out. So we have to always take care of this very important point in solving frames and machines, that whenever we are dismantling members, two meshing members or two connecting members, then the direction of reaction, if you have shown it to be positive on one part, then you have to show it in the opposite direction on the other part to satisfy Newton's third law. You have to keep this in mind. And so now let's draw the free body diagram of this sector gear. And you see that there was a pin connected at point H. So you have to show two reactions of the pin HX and HY. And you have to calculate this theta as well. Okay, this Ft is here. And what is this FAB? So let's see that this member AB is basically connected with the sector gear. So it is, as this sector gear rotates, this member develops a force in it, and that force is basically applied to the cylinder, causing compression of the cylinder. So we also realize that this member AB is basically a two force member, because we see that it is pin connected at both its ends and no other force is acting on this member. So we know that if it is a two force member, there is a reaction here, pin reaction here, and there is a pin reaction here in the y direction. Similarly, there is a pin reaction at B in the horizontal direction and a pin reaction at B in the vertical direction. And so we see that the forces are only applied at 2 points, two distinctive points, right? So the resultant force applied at A will be equal in value to the resultant force applied at B, and they will be opposite in direction. And their line of action will be the straight line joining point A and point B. This we have already studied when we studied the two force members, concepts related to two force members. So that is why, since the resultant force at A and B are same, I have shown the force in this member AB as a single resultant force FAB, right? And I have used a tensile direction, positive direction, tensile direction acting away from point B. It is also arbitrary, so if you want to assume a compressive direction, then okay, you have to use compressive like this towards point B. So compressive is towards point B, tensile is away from B. But if you have shown it compressive here, you have to show compressive here as well in order to satisfy the definition of two force member. The forces are equal in magnitude and opposite in direction. So for the time being, let us consider that this is tensile, and let us calculate this theta from the geometry. We know that this is 0.35, okay, and this distance is 1.2. So this angle is theta that we are calculating, and we can calculate from the value of tangent. So tangent theta is perpendicular upon base, which comes out to be 73.3. And now we realize that Hx and Hy are again not important for us. So we need to calculate the compressive force exerted at the cylinder. So this Hx and Hy is again unimportant for us. So we will going to write down the equation of movement in such a manner that these two forces are eliminated from the equation of moment, and that can only take place if we sum the moment of all these forces about point H, right? So if we will sum the moment about point H, then the line of action of Hx and Hy will pass from this point, and so they will not going to participate, they will not going to create any moment. Only the y component of FAB will generate moment about point H, and its x component will also not going to create any moment because the line of action is passing from point H exactly. And then this FD will going to create moment about point H, okay, and the moment arm being the radius of this sector circle, which is 0.35 plus 0.65 meters. So the y component of FAB is FAB sine of 73.73 multiplied by 0.35, which is the moment arm. Okay, and this is actually anti-clockwise movement, so that is why negative sign here. And similarly, FT is also a anti-clockwise movement. It is also exerting anti-clockwise movement about point H, so it is also negative, and its moment arm is 0.35 plus 0.65. So you solve this equation and you see you directly get the value of FAB. So FAB comes out to be 297.6 Newton, and this negative sign is indicating that this force FAB is not tensile, but it is compressive towards point B. So it is acting towards point B, not away from point B. But this does not mean that our answer is wrong. Just our direction was not correct. So now, since we have got this FAB, and you see I am not actually changing my assumption of tensile force, because I have assumed that FAB is tensile at B, so it will be tensile at A as well, acting away from point A. And you see that still these two satisfy the definition of two force members. They are equal in magnitude and opposite in direction, and they are collinear. So if you assume it to be compressive at point B, you have to assume it to be compressive at point A as well. If you assume it to be tensile at point A, you have to assume it tensile at point A. So I am sticking with my initial assumption that it is tensile. So here I have shown FAB to be tensile, acting away from point A, and this angle is 73.73. So these two angles are actually same, 73.73, right? And then if this table will going to exert a force on this cylinder S, then this cylinder will also going to exert equal and opposite force on the table. So that force is actually the force that we want to have. So I am using this Fs, the force of cylinder exerted on the table right here, because you see that cylinder and table are two bodies that are in contact, and whenever two bodies come in contact with each other, there is a normal force setup right at the interface. So this normal force is Fs, and this is what we are trying to find out. And these reactions NE and NF are actually the normal reactions at point E and point F, because you see that the table is in contact with these columns. As the table slide along this column, it is always in contact with the columns. So there will be a normal reaction at point E and point F. And so we see that I need to calculate Fs, so summation of Fx will be unnecessary for me. I only have to use summation of Fy, and you see if we sum the forces in the y direction taking the positive direction upward, then the vertical component of this force is acting downward, and this is also acting downward, so both of them are negative. So minus Fs minus FAB sine of 73.73 equals to 0 for equilibrium, and from this equation we can calculate Fs. So FAB, we calculated it to be 297.6, but remember that it was negative. Okay, so we have to use a negative sign here, right? So our assumption was that it is positive, but it turns out to be negative compressive force. However, we stick with our assumption of tensile force, but in the end, where we want to use the value of FAB, we will going to use its correct sign, minus. Okay. This concept was also used while we were solving problem on frame, if you remember. So Fs is 285.68 Newton, right? And you see that since this Fs is a compressive force and we have assumed it to be compressive here, the sign is positive, right? So 285.68, we have assumed the correct direction, downward, compressive, right, towards point A. So 285.68 Newton is the compressive force that this machine exerts on this cylinder S. So in the end, if you want to calculate the mechanical advantage of this machine structure, you can calculate it like output force divided by input force. So the output force was 285.68, the input was 40 Newton, and therefore the mechanical advantage of this mechanism is 7.142. So it is amplifying the force almost 7 times. So we have completed problem on machine. Let us move on to the next problem. This is problem number 6-115 of your textbook, and we are showing here a clamp, and we are exerting a force of 100 Newton on the clamp handle, and what we want to calculate is that we have to calculate the clamping force at point E. Okay, so you can imagine that this clamp is exerting a clamping force, which is a compressive force at point E on this block, and so this block will going to exert equal and opposite compressive force at point E, right? Let's move on further. So we see that in this machine structure we have no known load except the load applied at the handle at point P, which is 100 Newton, and so we cannot directly start our analysis by assuming or by considering this part of the machine, that is MANE. We cannot start our analysis from this portion, this part. Remember, we have to dismantle the machine, but we cannot start our analysis from this part BAE because there is no known load acting. So we have to then start our analysis from the member on which at least one known load is acting, and that is this member. This force 100 Newton is acting on this member, that is BCD. And so let us draw the free body diagram of BCD. So how we can do it? We have to dismantle this part, disconnect this part from its connection. So this is a pin joint at point B, this is a pin joint at point C, right, and this is a pin joint at point D. So we open all these connections and we draw the free body diagram of this member BCD, right? Please remember that we are using X and Y coordinates like this. Okay. So this edge is actually making an angle of 30 degree with the horizontal. Since BC and CP are at 90 degree to each other, then this member BC is also making an angle of 30 degree with the vertical. So it is just simply that you have tilted this horizontal axis by amount X dash, and so with an equal amount this Y dash is displaced, right? So this theta and this theta are always the same. That is why this is theta, this theta is 30 degree, and this theta is also 30 degree, right? And then since we have opened this pin connection, so we have to show its reaction at point B. We have shown one horizontal reaction Bx, another vertical reaction By at point B, and these directions are purely arbitrary. But you also realize that this member CD is a two force member again, because it is pin connected at point C and it is pin connected at point D. That is why there will be a force acting, a resultant force acting like this at point C, and there will be a resultant force acting like this at point D, and these two forces will be equal in magnitude and opposite in direction, and they will lie along the line joining these 2 points. So therefore I have shown them as one force FCD, and again I have used a tensile direction acting away from point C, right? This is arbitrary. So in order to find the values of Bx and By, because remember I have to move on to this part BANE, and in order to find the value of the compressive force at point E, I must know some value of force acting on this member, and that force will be the pin reaction Bx and By. If I can find out Bx and By, then I can use the equilibrium of this part BAE to calculate the compressive force at point E. So therefore my ultimate goal is to calculate Bx and By from this free body diagram. Okay, I realize that in doing so this FCD is no longer required. It is unimportant for me, and please notice that this known force of 100 Newton is neither acting on the x-axis nor it is acting on the y-axis, but it is acting on the y-axis. Right. So this angle is again 30 degree, and what I can do is that I can resolve this force of 100 Newton into its horizontal and vertical components immediately. So its vertical component will be cos of 30, and its horizontal component will be sine of 30. And since I do not require this force FCD, okay, I can sum the moment of all these forces about point C, and when I will do this, I realize that the line of action of FCD will going to pass from point C, so it will not going to create any moment about point C, and it will be eliminated from the moment equation. So therefore let us take the moment about point C of all these forces, and I am assuming a clockwise moment as positive. So the moment arm of this force, 100 Newton force, from point C is 160 millimeters, or it is 0.16 meters. Okay, this force P is acting 90 degree. As you can see here, it is acting 90 degree on this edge, on this member. So its moment arm is directly given to be 160 millimeters. That is why it is 0.16 times P, and this is a clockwise movement, so therefore positive sign with it. Similarly, we have to calculate the moment of Bx at point C, and its moment arm is this vertical distance. So this member, this edge is 60 millimeters in length, and so therefore this thing is 60 and sine of 60. Okay, 60 sine of 60. So 60 millimeters, therefore it is 0.06 meters. So it is Bx into 0.06 sine of 60. Then of course you have to calculate By as well. You have to calculate By as well, and the moment arm of By is this distance, which is 60 cos of 60. So 0.06 cos of 60, and these all moments must sum up to 0. So you have this equation number 1, in which you have Bx and By, and you cannot do anything further, so we must have to apply one more equation of equilibrium. But we see that if we are going to apply summation of Fy, then FCD will going to appear in summation of Fy, which is really not wanted. So we are going to use summation Fx equals to 0. Instead of using summation Fy equals to 0, we will use summation Fx equals to 0, and this will directly going to give us a value of Bx. So you see that Bx is acting in the positive x direction, so positive sign appears here, Bx, and then the horizontal component of P was P sine 30. So it is also acting in the positive x direction. So it's P sine of 30, Bx equals to 0, and from this equation we get that Bx is minus 50 Newton. And this minus sign is showing us that our initial assumption of this direction was not appropriate. It is acting in the reverse direction. So let it be like that, and then you substitute Bx in equation number 1 here to get By, which comes out to be minus 446.83 Newton. Again with a negative sign, this means that our initial assumption of By is incorrect. It is not acting upward, instead it is acting downward. So now we have the values of bx and by. So what we will do is that we are in this position to now draw the free body diagram of this member BAE, because we know that now we are familiar with the values of bx and by, so we can draw the free body diagram of BAE. So here I have shown the free body diagram of member BAE, and at this point E, this block is exerting a compressive force at point E, and if we are able to find this force Fe, then it will be equal and opposite to the force exerted by the clamp on the block. This is because of Newton's third law. So let us disconnect uh, this pin and this pin at A, okay, and redraw this member BAE here like this. Show all the necessary dimensions. This angle is 45 given here, okay, and you should remember the point that I told you in the previous problem, that since I have shown Bx and By to act in the positive x and positive y direction on member BCD, okay, as you can see here, then since member BCD and BAE are connected together with this common pin acting at B, so if I have shown this direction Bx and By to be positive towards positive x and positive y on member BCD, I have to show them in the opposite direction on member BA and E. So please notice that I have shown here Bx to act in the negative x direction and By to act in the negative y direction, whereas when I draw the free body diagram of member BCD, I showed both of these forces to be in positive direction, and this is because when I will combine these two members together by joining this pin, these reactions Bx and By will going to cancel out internally because of Newton's third law. So this is an important point that you have to remember while you are solving frames and machines. And now we just have to use submission of moment about point A. So submission of moment about point A, we will going to use, and we see that in doing so Ax and Ay will not going to produce any moment about point A. The only forces that will going to produce moment about point A is Fe, By and Bx. So Fe has a moment arm of 0.075 from point A, and this is actually clockwise, so it is positive. Then By has a moment arm of 50 cos of 45 and 50 millimeters, so it is 0.05 meters cos of 45, okay, and this is a clockwise moment, that is why positive. And Bx has a moment arm 50 sine of 45, okay, and this is anti-clockwise, so it has a minus sign here appearing. Bx 50 sine of 45 equals to 0, and from this equation of moment we can directly calculate the value of Fe, because Bx and By are already known to us. And please remember that since Bx and By both comes out to be negative in the previous slide, we have to use that negative sign here with their values. So when I inserted the value of By, I use a negative sign. When I inserted the value of Bx, I use the negative sign, right? And so therefore I got the value of Fe to be 187.067 Newton. And you see that the force of the clamp on the block is equal to this force and opposite in direction. So this is how we solve the problems on machines. The only thing to remember, which is very vital and important, is that whenever you are dismantling members connected by common support, you have to show the reactions in opposite directions, so that when you again combine or join the members, the reactions internally cancels out. Okay, so we will going to meet in the next lecture. Thank you.